here today to talk to you about VisIt. At Livermore, I work in the Weapons Simulation Computing program, and in that program, we build large HPC physics simulations, and we build tools to help with the workflow of those simulations. One of those tools is VisIt. And I've been working on VisIt for almost 10 years, being a user and a developer of VisIt. I'm the software architect of VisIt, and that's what brings me here to teach you about the tool today. So the talk is going to be probably a little bit of a whirlwind at the beginning, and then I'm going to try to slow down for a pseudo hands-on. All the material that we have here is hosted on our VisIt users wiki, so if I go too fast, there's reference there to go back to it. But I'm going to start with a quick introduction, give you a little bit more information about the project. The introduction will be focused on the project since Joe did a good job of setting the stage on some of the visualization concepts. I'm going to then transition to give you a tour of the tool with some dummy example data, and then we'll drop into this exploration of an aneurysm simulation, which will be a little bit better paced if you want to try to follow along. There's a bunch of additional hands-on material as well on our wiki site. So there's a good hands-on that's exploring a water flow simulation. There's a volume rendering tutorial which can give you a little bit more information about the different volume rendering options that we provide. And finally, there's an advanced movie making tutorial, which is something that we have that's new that actually kind of talks about some of the concepts of putting together a really nice movie. Joe talked about using image magic and basically composing a whole bunch of things together. This movie making tutorial gives you an example of how to do that. So again, the resources are all on our VisIt users wiki site. I'm just going to go there real quick. So here it is. And if you search for tutorial, you'll land there, but there's also this VisIt tutorials. And in particular, for this particular presentation, everything you need is here under the app task section. All right, and one more thing. So the Aneurysm Data set was provided to us from some colleagues from Swiss Supercomputing Center. This was simulated a few years ago using the Life5 finite element solver, and I guess it came out of, in Europe, there were a bunch of people kind of rising to the grand challenge of simulating aneurysm data. And they made that data available to us, and we've been using it for several years, and it works for a really good, nice, hands-on, sort of narrative-based tutorial. So we're very thankful to them for providing us that data. All right, so on to the VisIt project introduction. And the first aspect of that is something that I always talk about. VisIt was created before Google. Google became popular, and it was not created by marketing or branding geniuses. So if you Google VisIt, you may not find VisIt, although when I Google VisIt, I do find it. So if you are trying to find out information about VisIt, visitusers.org is a good place for it. And also, if you search for LLNL VisIt, you'll get to the right place. And then, whenever I do this, I figure out what Google thinks I should be doing. It thinks I should go to Museum of Science and Industry, or maybe I should go to Florida. I'm actually from Florida. I haven't been there in a while, so maybe it knows those things. I'm not quite sure. All right. So what is VisIt? So VisIt, like ParaView, is a open source turnkey product application for doing visualization of primarily mesh-based data. It's something that scientific simulation people who are running scientific simulation codes use to visualize their data. It's something that people who are writing scientific codes use to help them debug things when they go wrong. And it's also used by visualization experts like myself to produce really nice movies. It's more than just an application. It's actually kind of an infrastructure for doing parallel post-processing. And I guess to answer your question earlier, so VisIt and ParaView are both built on VTK, but the thing that both VisIt and ParaView bring is this distributed parallel domain decomposed sort of model on top of VTK. VTK by itself doesn't provide that. So they have different ways of doing that. And in many ways, that's the big challenge for HPC is how we handle that parallelism. It's open source. It's released under a BSD style 3-clause license. And so Joe also did a really good job of showing that visualization tools are great for other things than just producing movies. But I always like to hammer this home. VisIt's used for a lot of different use cases. Not every simulation, don't tell your simulations this, but not every simulation is destined for the cover of Nature or destined to be a beautiful HD movie in a showcase. Usually, your simulations are their simulation data is sort of at the whim of the person who ran the simulation, and they're going to go in and slice and dice it and transform the data. And so data exploration is really what people do primarily with a tool like VisIt. Another use case that we have is quantitative analysis. So pictures are great, but oftentimes things can be very, very communicated even better with a single curve, right? An integral curve, especially in the physics world, if you're trying to compare with theory. So we have tools built into VisIt to help you do quantitative analysis and summaries and integrals and things like that. Another use case is visual debugging, and Joe showed an example of this as well. But it's really nice whenever you're writing a really complex simulation code. If you have a crash, you can get into a traditional debugger, but often you can get really good intuition if you can go into your code and go in and look at your mesh and see where things are going wrong, where a mesh is tangling or something like that. So there's lots of features in VisIt to give you rich information to help you with visual debugging. Another use case is comparative analysis. So this goes from just kind of eyeball norm, produce two pictures and look at them and see if they're the same. But it also goes beyond that, where we have ways of mapping meshes onto each other and taking differences, so you can make that more quantitative. And finally, presentation graphics are important. So making nice movies, making nice plots, the power of visualization and communicating from these really nice images is very important. So that's another use case that we support. And this picture here that I have under presentation graphics is actually a snapshot of the advanced movie making tutorial that I mentioned earlier. So we're an HPC code. How do we do that? We use MPI. So this cartoon, well, it's not really a cartoon, it's an actual data set, but this conceptually gives you a good idea of how we do those things. So if you imagine your simulation code as being one giant volume that's being simulated, it's subdivided into domains, which are subdivided more into computational zones or cells. So the full data set you see here on the left is a famous Raleigh-Taylor mixed simulation from several years ago. And computationally, it's sort of represented on the right into these subgrids, and each subgrid has little zones. So we use MPI in order to process the data and render the data and give you the picture on the left, even though it really is represented like you see on the right. And we're also, with the changes to the supercomputers that are coming and the changes to the, particularly heterogeneous architectures, we're working on supporting VisIt's pipelines so they can do things with threads or in many core devices like GPUs. One key aspect to that is a new product called VTKM, which isn't VTK, but it's related, which helps to deal with performance portability on GPUs and many core processors. So we're working on integrating those things into VisIt. This is the history of the project. So VisIt started about the year 2000 at Livermore, and then it was focused on supporting the simulation codes at Livermore. So those codes were big. They needed a tool that could handle distributed domain parallelism and produce pictures for them. That's where VisIt came in. So a few years in, we started to expand out past just the ASC money and the Department of Energy ASC money, and we started to have different funding opportunities in Office of Science. As part of that, we were able to transition VisIt to an open source tool, and in 2008, we moved to a fully open source repo. And from there, we've been growing more with more collaboration. So there are several different organizations that are involved in VisIt development. Livermore, where I'm from, was where it was born. We have about we have 6 people actually who are working on VisIt there. But there's about 20 people scattered around, mostly around the US, but there's a few people elsewhere who also contribute to VisIt. So VisIt's data model is built on VTK, but there's some swizzles to that. From your perspective, you can think about it as it has a lot of different computational mesh types that you would care about writing a physics code. And it supports a lot of different field types that you would care about, such as scalars, vectors, tensors. And there's also some things that are a little bit more exotic, particularly in mixed material codes, material volume fractions. When you're dealing with multiphysics, those come in. And species or mass fraction data. There's specific capabilities to support those. This is the corollary to Joe's slide of there's a whole bunch of different file formats everybody uses. VisIt supports more than 110 different file formats. The biggest question you get is, how do I get my data into VisIt? I think, so if you're lucky, you're already writing to one of those 110 different file formats. If not, there's a couple easy ways to get going. The first thing I would do is that there's a very simple standalone C-based utility called VisIt Writer that can do just very basics, write VTK files. That you could toy with that and get an idea of how you could create data sets. Or I would, and eventually I would support transitioning to a more widely used file format. So VTK is very widely used. Silo is what we use for the majority of our codes at Livermore. XDMF is a popular option as well. XDMF is basically you provide an XML schema that describes what type of mesh and field information you have in HDF5 files. So that's a good one. If you already have HDF5 data, you might be able to write this XML file that tells you, hey, these are my meshes. And then also parallel VTK is a good option as well. The more drawn out answer is there's a 200-page manual that tells you how to do this. That's so there's good documentation about it, but it can be complicated. So I'd be happy to talk with you in depth about your particular situation during the hands-on or what have you. So VisIt scales up and it can run in parallel. How does it do that? It uses a client-server architecture. This gives you an understanding of how that works. There is basically the VisIt viewer coordinates everything, and that can be run locally on your desktop. And there's various clients to this, one of them being the GUI, one of them being our Python command line interface. And that viewer can talk to a parallel engine, a parallel resource that's running on a remote HPC cluster. So the engine can pull in all the data, the engine can parallel process everything with MPI, and it can do scalable rendering and all those things. So, to build a distributed memory parallel tool, you have to put the pieces of the puzzle back together. That's fundamentally what it's about. And this is an example of rendering and how we do that with rendering, just the concepts of how we do that with rendering. Each process, when we run in parallel and we do parallel rendering, will produce one piece of the puzzle. And we have to composite those back to get the image that you're expecting. So this is for surface rendering, but we also have different algorithms that help us do scalable volume rendering and things like that. I mentioned this before, but VisIt isn't just an application. It can be used as an infrastructure. So it's extensible. Certain things can be extended in C++. Certain things can be written in Python. We also have an in situ library called libsim that allows you to link the whole of VisIt into your simulation and avoid writing files. Libsim, as is now, is kind of a heavyweight solution because VisIt is a big beast. So we're working on producing a lighter weight capability for in situ visualization that that's a current thrust area that we have. But the thing to think about here is that, if you don't like, exactly what VisIt's doing with its file formats, well, you could extend it and you could write your own file plugin. If you need slightly different analysis capabilities, well, you might be able to write a Python query, for example, to get those things out. And this is my last slide on the VisIt introduction. With content here. So it's also used as a platform to deploy visualization research. So this goes hand in hand with it being an infrastructure for doing these things. VisIt, has this nice distributed parallel model, and it has pipelines that support those things. So visualization researchers use VisIt in order to develop new algorithms in this domain, and they also use it as a way to deploy algorithms for that. One of the greatest examples of this, most successful example of this, is our parallel streamline capability or pathline capability, which was developed to be a general capability to help the Fusion community, and it all runs in parallel, and it's been given to different user communities through VisIt. So we have a lot of different research collaborations, big ones in Office of Science, Oscar, and our current focus is on lightweight in situ processing, node level parallelism, so again, that goes back to VTKM, leveraging that new tool, new algorithms there, and of course our distributed memory parallel algorithms, because that's really where kind of the bread and butter of HPC comes in. In summary, VisIt's a production tool. It's been around for a while. It has a vibrant community behind it of both developers and users. It provides features for folks who are running simulations, folks who are writing simulations, and visualization experts who want to make nice movies on the biggest supercomputers there are. So with that, I'm going to transition now into a tour of VisIt's interface. This tour is pulled from some longer tutorials that we have on our wiki page, so there's good references there. So I'm going to start up VisIt. When I start up VisIt, you will see two windows that pop up. This window over here is the GUI, and I realize this is hard to see a little bit, so I'm going to try to zoom in. But this window over here is the GUI, and that was where you drive up setting where you open your databases and set up your simulations. And this window here represents the viewer, which is again the thing that's managing our state and producing our pictures. VisIt has 5 primary abstractions that help you to think about whenever you're using the interface. The first is a database. That's how we read data in. The second is a plot. That's how you see the data after it's read in. The third is an operator. Operators allow you to transform the data in some way. It might be slicing, dicing, et cetera. The fourth is an expression. An expression allows you to create derived quantities. So an example of this is maybe you have a simulation that saved out its density, but you don't have the mass, and you'd like to calculate the mass on the fly. Well, you can define an expression that scales the density by the volume of the mesh to get the mass on the fly. That's what we mean by expressions or derived quantities. The fifth one is our queries, which are data summarization operations. What's the integral of my mass, right? Total mass, things like that. So in going through this, I'm going to show you all different aspects of those 5 building blocks. The first one's a database, and here there's a little open button. So I'm going to pull some example data, which is available via our website. And in this case, I'm going to open example.silo, which is aptly named. Oops. So this window here allows you to browse the file system. It also allows you to browse remote file systems in a client-server mode, which I'll show you a little bit later on. So let's see. I'm going to get my most favorite example, example.silo. I open it up. My laptop's configured to run an MPI in parallel, and because of that, I get this window that asks me if I want to run serial or parallel mode. You probably won't see that out of the box on VisIt, but in this case, this is a simple example data set. I'm just going to run it serial. All right. So I opened the file, and the first thing most people say is, great, something went wrong, because I don't see a picture on my screen. And everything's probably okay. If something went wrong, you would get a pop-up box that said something went wrong. This is by design, so because we're usually dealing with big data sets, we want you to tell us what you want to do with them rather than read your mind whenever we actually plot things. It's just a design decision that's been there since the beginning. In order to view the data, I need to add a plot. Again, plot is our second sort of core abstraction that we use in VisIt. And there's this over here. Let me see if I can make my cursor big. Yeah. Over here, there's a little add icon by the plot list. And these are all your different plotting options. The most common option that people use is pseudocolor. It's sort of the bread and butter of scientific visualization. And I'm going to plot, this list here gives me all the variables that exist in my data set. You can't really see them that well, but I'm going to plot the one named pressure. And I've added a plot now, and it's green. Green means it's ready for me to draw it when I say it's OK to do so, which I will now. So I draw. And this is my example data set. So you can see it here in the viewer. We have, and we can look at the computational mesh by adding a different type of plot. That's called the mesh plot. So if I go to add mesh and draw that, you can see the different elements that are used to decompose this data. And this plot list here allows you to set up as many plots as you'd like to with all kinds of different options and things. If you expand, there's a little arrow here to expand the plots. You can double click on them. In our UI, we basically have these attribute windows that give you different options for setting up your plot. In this one, I have the pseudocolor attributes here. I can do things like change the range that I would like to plot. So let me cheat by looking at the color bar here. So say I really wanted to peg the range between 4 and 5 for some reason, I could do that. If I hit apply here, then you'll see that my visualization changed to basically only show those ranges. Similarly with the mesh plot, there's lots of options for how your lines look and things like that. So next thing I want to show you is what an operator is. I'm going to delete this mesh plot for now. So there's this add button over here on the left for operators, and they're categorized by the different types of things that they do. In this case, we're going to add a slice operator. That's under the slicing category. When I add that and I draw, I now have a 2D slice that was the part of my data that I was looking at. Where did I slice? Well, if you look at this, if you double click over here, you see these slice options. I happen to slice on the y-axis here, and you'll notice this is a 2D mode of navigation here. If I wanted to retain that slice in 3D, there's an option here. I can uncheck project to 2D, and I can see where that slice was in 3D space, and I can change which axis I sliced, things like that. I'm going to project it back to 2D here to show you some of the different interaction modes. So in the viewer up here, let me just show this bar. These are the different kind of navigation modes that we have in VisIt and interaction modes. This is, by default, we have navigate mode, which allows you to spin things, zoom in. We also have a zoom mode, which would allow me to zoom in, to a particular box. There's different types of interactions, such as a zone pick. If I click on this, I'm going to get, basically where information about that particular element or zone or cell. Those things are all pretty overloaded in this community of my mesh. So when I click on that, I did a pick, and I get the different pressure values that I plotted over here. There's tons of options for diving in deeper. There's also a node pick. So it gives me a slightly different view of the data. It picks the nearest node, or the node it intersects, instead of the nearest zone. Sorry, yes, that's right. Another important feature we have is a line out. So that's this here. So that allows us to click and drag across our data. And when we do that, we get a line of the values that pulled through that. It's easy to do that in 2D. In 3D, there's a query that allows you to set a 3D line to do the same thing. All right, I'm going to show you another operator that's very handy. So that's the Isosurface operator. So again, under operators here, Isosurface is also under selection. Joe showed you some examples of this, but basically you could think of this as pulling out surfaces of constant value in your fields. By default, if I plot this, the Isosurfaces is set up to just pull out 10 different levels from across the data set. You can change that to be the values or what have you. And you can, in this example, you can actually isosurface by one variable and display on the mesh another variable, which is another example that Joe showed you. You might want to slice something by one variable, but you're interested in that variable, another variable in the output. So in this case, I'm plotting the pressure, but I could actually slice my isosurface by the temperature and get a slightly different set of contours out. Another thing is so in VisIt there's also a contour plot, and I kind of want to talk about what the difference between these two things are. So you'll see here I added another viewer window. VisIt allows you to have multiple viewer windows, and up here, this in the GUI, this right here, this active window 2. Sorry, let me make my pointer big. I can't. The active window 2 tells you which one you're controlling at any time. So I just added this new one, and if I look here and I add a contour plot. I can add a contour plot of the temperature. The contour plot does a similar thing. It does an isosurface, but it labels them using a discrete color table, so you can pick out the things. So, whereas on the left, I'm doing that isosurface operator, but I'm coloring it by pseudocolor. This gives you an idea of how some of the building blocks can be intermixed. Different filters like isocontour can be visualized different ways, and that's why we've separated the plotting from the operators and things like that. Okay. Another plot I want to show you is the volume plot very quickly. So volume visualization. And by default, it shows up, it's using a GPU accelerated sort of simplified way of doing volume rendering, which we call splatting. There's a bunch of options here. One of the way to make nice pictures out of volume rendering is with this ray casting compositing. It's pretty expensive, but it creates nice pictures. In volume rendering, the hardest thing you need to do is you need to be able to set a transfer function. It's sort of how, as the rays go through your data, you're going to represent the colors when they intersect things. So as part of the volume plot, you have this widget here that allows you to select different pieces of your data based on the scalar range. And if I click here and I do a volume rendering, again, it's doing the expensive version of volume rendering here. It'll take a minute and it'll come back and it will give me a picture that's basically integrating through my whole data set. All right. So I changed the transfer function a little bit. We'll look at it a little bit differently. This volume renderer also works in parallel, but volume rendering can be a pretty memory-intensive thing. So, so you have to. It takes a lot of playing with to get it to work, especially on a very large data set. All right, so I've showed you a lot about plots, operators, and databases. I want to talk to you a little bit about the last two things. That's expressions and queries. So expressions, again, allow you to do derived quantities. You can get to how we define expressions in VisIt by going to the controls menu, expressions. And here, I already have one defined, but here you have an editor that allows you to basically create new variables. The names you put into this will become plottable in the menu. And in this example here, I've defined a new variable called G. Let me zoom in. And what I'm doing is I'm taking the gradient of the temperature here. So this defines a new vector variable on my data set that I can plot. And I can also create another variable that gives me the magnitude of my new vector variable, and I can plot that as a scalar value. So we define that expression. And now when I come back out here, that Gmag variable is now something that's plottable by my pseudocolor plot. And I hit draw, and you can see now I'm looking at the magnitude of the gradient here, the gradient that I just computed on the fly. So queries are the last piece of the puzzle. So they're also available under the controls menu, so controls query. There's a whole list of different types of queries here. They're actually sort of grouped logically by the types of things that they operate on or that they're involved with. So for example, curve-related, mesh-related, things that are related to the variable, et cetera. So that can help you winnow down this really huge list of queries. In this example, I'm going to just do a very basic query. I'm going to do the max. So this gives me the maximum value of my data set. So it gives me a textual result. It says, OK, here's the max. It was this value, it was at this coordinate, things of that nature. So we're almost getting to the point where I'm going to transition into the other hands-on, but I want to cover something else really quick. So Python. Python's a very important piece of VisIt. It's a very important aspect of it. It's used for all of our batch scripting and really scripted analysis. So in VisIt, there's a couple different ways to use Python. The one I'm going to talk about here is we call the Python client interface. That allows you to drive VisIt as you drive. I have been driving it in the GUI. So anything you can do in the GUI, you can do in the command line Python interface as well. And I have just a couple examples here, scripts that I'm going to walk you through. Actually, I'll probably just show you one script that kind of shows you the example of how you can use Python to set up your plots. So in the interest of time, I'm going to look at this one. So if you're looking at the wiki pages, this is called listing for using all of VisIt's building blocks. So the reason why I like this example is in about 30 lines of Python code, you can see how we can use all 5 of those things that I just talked to you about. Make it a little bit bigger. Oops, I really was small. So we can add a plot. In this case, at the top, I'm adding a pseudocolor plot of temperature. You saw me do that in the GUI. We can add an operator. This operator is like a slice operator, but it takes 3 orthogonal slices instead of 1. That's why it's called the 3-slice operator. I set that operator's attributes. I can run queries. So you saw me run the max query from the GUI. I can say query max and get that same example out in the command line interface. I can define expressions. So this is defining the gradient. This is what you saw me do through the GUI as well. And in this case, I'm going to add another plot, which is a streamline plot of that gradient. So let's run this so you can see the output. So there's a couple different ways to get at this command line in VisIt. One of the easiest ways is under Controls Command. There's a window here, and this window serves as a scratch pad for Python scripts, and it also allows you to record GUI actions and turn them into Python scripts, which is a very valuable feature. I'm going to run this example, which I have sort of basically, I'm just saying, please run this Python script, where it happens to be on my laptop here. And if I execute it, the Python command line will pop up, and I get this plot that was created by that script. So incredibly powerful. again, the fact that you can record and get Python code back out is very, very useful. There's a 300-page Python manual, but again, not many people read 300-page manuals anymore. So I'll just show you an example of how we can record something here. So in this commands window, I click record. Okay, this is sort of your standard macro type of GUI interaction where you record things and then you come back in here and you say stop and you get the Python that talks about those. So in this example, I'm going to go and I'm going to change the color table that I'm using for my first plot, which was that 3-slice plot. I'll change it to something else. So I change those attributes. I come back here. I hit stop. And it's going to give me, basically a recording of the attributes, which you can use to replay. It's a little verbose because it's recording the full state. If you've mucked with anything, it wants to capture it in a reproducible way. So when you get the hang of this, though, you can go in there and you can slice down the things that are recorded and kind of productize them into a simpler, more maintainable script. All right, and now, so I'm gonna show client server a little bit later. But the thing that I always forget to show, and is the most important thing, I need to show you right now. How do you save an image with VisIt? I get too excited, so I forget to show people this sometimes. So, so once you have your plot set up and you're ready to render a PNG or render a movie out of it, we provide different ways for doing that. So in this case, I'm just going to show you how to save a file. There's also a movie wizard that walks you through the steps of creating an MPEG or something like that. So under VisIt, there's under the File menu, when you click on the GUI, there's Set Save Options. And this gives you a whole bunch of, let me get this back. This gives you a whole bunch of options for what your file name would be called, how big you want the resolution to be. It doesn't have to be the same size as what you're looking at on your screen. And there's a Save button here. So if I click Save, then I will get this thing that says, I've created VisIt 00001. And it told me here that it was nice enough not to stomp on a file I already had that was VisIt 0000. But if you go to the file system and you look, it should be in my home directory. If I open that file, then you get the render. All right, so that's it for the tour. So in the interest of time, I'm going to move into looking at this aneurysm simulation, but I'd be happy to take questions during the hands-on and things like that later. So for the aneurysm simulation, it's also on the wiki page. And if you go here, we will actually probably get through part of the first 2 sections of it. But there's much more details there for you to dive into later. Let me get my cheat sheet so I remember what numbers to type. All right. And in this example, let me close these things down. This example, we're going to be using this aneurysm simulation, which came from the Life5 solver. And it's really just a subset of the simulation. I sort of packaged it down into the best I could get for 500 megabytes. It has about 200 time steps, 2 variables per time step. And it's all those times things are kind of compressed using Silo, and there's one file that groups them together. It's called the .visit file. I can open that one file, and then I get access to these 200 different time steps. So let me open the data set first. All right. And let me give you a little bit of idea of what we're looking at here. So if we look at the mesh of this data set, if I can click correctly. If we look at the mesh of this data set, this is the computational domain. It doesn't change over time. So this is an Eulerian type simulation. You can think of it that way. And it's packaged in a way where I have 2 variables in the mesh just so you could download it in under 500 gigabytes, or 500 megabytes, not gigabytes. If we look at this, we could go through and we could look at different mesh options for coloring it, making the mesh look bigger. I have 200 time steps, so I have this time slider here is now active. But again, the mesh doesn't change over time, so me plotting the mesh over time isn't going to be too exciting. Let's look at the variables that we have available in this data set. So there's two, there's pressure, and then there's a velocity. Velocity is a vector field, but VisIt automatically defines an expression for me for the magnitude of that vector field, so I can plot it. If I plot pressure here, you can see here's the pressure field. And if I play, you'll notice it will, things are definitely evolving over this 200 time steps here. Still maybe not too exciting. So when you think about a heart simulation, what's sort of the canonical thing you think about from a heart? If you go to a doctor, what does a doctor usually do? The most basic thing for your heart, right? What do they usually do? Yeah. Heartbeats, right? So if we're doing an aneurysm simulation that's being driven by something that looks like a heart, we should be able to pull out that signature of a heartbeat, right? The signal that's driving it. We don't have a heart here. We only have a small artery here. But assuming they did things correctly, then you're going to have a heartbeat somewhere involved in the equation. So we can use VisIt's query infrastructure, and we can do a query over all these time steps in order to look at the max pressure value or the max velocity value. And that will be a good proxy for that heartbeat. So I'm going to show you how to do that. One thing I want to do before that is under controls, there's query over time options. So query over time is going to run my query that gives me one value across all these 200 time steps and give me a line back. I need to pick the x-axis for that line. So when I created these data sets, I basically they have the time values in them, but they don't have cycles. Cycles are just another diagnostic information that people usually put out. Cycle 0 in all of them. So by default, VisIt will have that x-axis be the cycle. And if cycle 0 over all 200 time steps, you're going to get a vertical line. So we change that by changing our query over time options to actually use the time. And again, this is under the options menu. You can get to query over time. I'm just going to change this to time, apply that, and then I'm going to do my query. So controls query, oops. And I'm going to use that same max query you saw me use earlier, but I'm going to click this button here that says do time query. Let me just show you. And there's different options here. You can set striding, you can change the range. I'm just going to let it go with the whole thing. Hit query. Now it's frantically reading all 200 different time steps and doing this query to pull out this value. So it takes a little bit of time. And here we go. So here's our signal that we got out of the max over time. So how many heartbeats does our window of this simulation encompass? 2? Yes. All right. So we looked at the pressure. I mentioned there's also velocity here. If I plot the velocity magnitude, that gives me the magnitude of the velocity vector. You notice there's not really too much interesting happening here, thankfully. It was the walls of the simulation, the velocity is 0. There is a whole lot going on inside, though, right? So you can see that from this inlet. So how do we get in and how do we dissect this data and look at it? Look at it from, get a better idea of what's happening inside here. There's a couple different ways to do it. It's a vector field, so we're going to go into some vector field visualization stuff. The first thing we can do, though, is we can just look at isosurfaces of this value. In doing that, though, you'll see. So if I do a selection, add an isosurface operator. Again, that's under operator slicing isosurface, and I'll set it to some values that I know, happen to exist in this data set: 10, 15, and 20. If I draw this, I'm going to kind of lose track of really where I am in this simulation, right? So this is where I have high velocity over time throughout this data set, which is good, but I think we kind of lost a little bit of the context of where this is happening in our artery. So in order to combat that, I'm going to add a second plot, and that will be it's basically going to be a plot of the mesh. I'm going to add it through our subset plot, which is, it's just simpler to set. You could also add a mesh plot. It's simpler to set the options for what I want to do for that here. And I'm going to take off. I'm going to uncheck this apply operators to all plots, and I'm not going to do my isosurface on this mesh. So I want to keep this whole mesh here, and I want to make it transparent so I can tell what's happening where it's happening. So I add this plot, and I'm going to basically color it by a nicer blue color, and I'm going to set my opacity way down low. And when I do this, I'll actually have an idea of where this was happening, in my simulation. And then when I animate it, for example, I'll have better context for what's going on. If you want to, you could, knowing that signal of the heartbeat, you could sort of have that standing next to this, so you have an idea of where the driving forces are actually causing things to happen in this. We talked a lot about isosurfaces. There's also a nice feature VisIt has called an Isovolume, and what this allows you to do is it allows you to basically extract out subvolumes of your mesh between two ISO values. So an isosurface gives you a surface. I need isosurface of 15. Okay, I'll get this nice surface that gives me a field where all my values were 15. But what if I really care about the volume where my velocity is between 10 and 15? I care about some volumetric region. You can use an isovolume operator to do that. So that is another option under operators. I'm going to take off the isosurface. Before we do that, I'll just, to give you an idea, let me zoom in here. So you can see, that there's surfaces here now. If I instead add an isovolume operator, which is actually under selection, I can set two different ISO values. So in this case, I'm going to set it between 10 and 20. And when I draw this, I'll have the volume left out there. So I'm just pulling out this subvolume. That's really good for certain types of analysis. Again, you have some way of identifying some feature, and you want to know the volume of that feature. You want to know the mass of your feature. Isovolume is a better way to do that than an isosurface. All right, so we looked a lot at plotting pseudo-color plots, plotting surfaces of this, but really fundamentally underlying this is a vector field. So we'd like to look at the vectors. And the way we do that is with glyph plots, like Joe mentioned this morning. So if I go to add plots, under my plot options here, I have an option for my velocity vector. And if I draw this, I'm going to get kind of a sparse looking plot to begin with. This is, again, another one of these things by design. Glyphs are expensive, so if you try to plot, a billion glyphs, you're going to be in for a world of pain. So we try to tune things down so you don't get yourself in trouble right at the beginning. In this example, the defaults really just have this set, so we're only drawing 400 of those possible things, but we can set that to some striding to get more of them drawn. And there's other things we can do to make them look nicer. We can scale them to be a little bit bigger, and I'm going to maybe change this to a cylinder instead of a line, so they'll just look a little bit nicer. Put this to high. So now I have a bunch more, I have a lot more context than I'm seeing in my plot. I'm going to change the color map to something else. So now I can animate this, and I can see, let's see, I'm animating the wrong thing. Ooh, here we go. Hold on a second. Let me go back to time. So if I animate this, I'll see these vectors, slowly changing over time. The vectors give me an instantaneous view of what's happening in this flow localized, right? So at each point in the simulation, I have a velocity vector that's part of the field. So that's sort of helpful, and animating them over time is helpful as well, but we can go beyond that. So VisIt provides a way to do both streamlines and pathlines. So streamlines are, if you take some seed points and you drop them in your simulation, streamlines will be advected, and the streamline context is really, it's a steady state thing. So streamline says, given that time step, if it was steady state, where would these particles be advected? Pathlines takes into consideration the fact that the velocity or vector field changes over time. So to show you how to do both of those, and there are differences in them. In order to do this, you need time data, between your simulation files and things like that. This particular data set does, you'll notice it has, you're seeing here the times moving here. So, and those times make sense with the velocity vector field. They should all in your simulations too, because that's how you, because you're doing slightly more physics than we're doing. Although we do have some good different types of integrators and things like that for our streamlines. So I'm going to delete this velocity vector plot, and we're going to set up a streamline plot first, and then we will transition that to a pathline plot. So the first thing you need to do when you're doing streamlines is you need to be able to pick a where you want to put these seed points. So you can think of it as where you want to put drops of dye or smoke, or smoke lines of smoke over your wing of your airplane or something like that. So you need to put these points somewhere. And in our example, we're going to put them around this inlet here. And we could sort of arbitrarily pick a point. That's fine, but instead I want to kind of show you how you can use, again, VisIt's query infrastructure in order to get a better idea of where to place it. So I'm going to add another plot, and this is going to be a pseudocolor of the velocity magnitude. And I'm going to slice that right over here, kind of right through here, and look at that localized field. So I'm going to add a slice operator, and I happen to know where that should go, or my paper happens to know where that should go. So I'm going to do it basically through 333, and it should be ready to draw now. And oops, I forgot one step. So VisIt's yelling at me because I'm trying to plot a 2D plot and a 3D plot in the same window. To get around that, I just uncheck this project to 2D. And okay, so here's my inlet, right? Here's my slice. And you can see, well, it's a little hard to see on this projector, but this isn't really a perfectly uniform thing. The peak of this signal isn't, I couldn't, it's at some non-uniform value. I couldn't set it really easily by hand. But what I can do is I can ask where the maximum value is of this slice. So if I go to controls query, I have that velocity magnitude slice selected. I can ask for the max, and let's see here. It should be the same. Yeah, okay. I can ask for the max. There's two different options here for this query. There's original data and there's actual data. This is confusing but useful. Original data gives you just as it came out of the file, and actual data gives it to you whatever you happen to see on the screen. The reason why they're there right next to each other is people do things often where they like to ping back and forth between the two. They like to say, what was it? What did I do to it? In this case, I look at the actual data. I do a query, and it's going to tell me that this velocity magnitude lives at a particular spot. So that particular spot, I sliced on 333. But that particular spot happens to be here, on that plane. So three is we expect one of them to be 3. All right, so this is the value that I'm going to use to set my seed points for my streamline. So let me try to copy it. And I'm going to add a new plot. This time I'm going to add a streamline plot. And it's going to be using the velocity. And there's a ton of options here. This section here is really focused on where you're putting those seed points. In my case, I'm going to seed a circle. I'm going to seed a circle around those values that you saw me do with my query. Doesn't like commas, so I'm going to take them out. I'm going to change the normal of this circle and then the up axis to make sense with my data. We want things to be going into this inlet. And I'm going to set my radius to be something a little bit bigger, or actually a little bit smaller. So if I don't do this, I'm going to have seed points outside of my problem, and then they're not going to go anywhere. So you'll see in a second where these seed points live. But let me get them set up. All right, and there's a couple other things I want to change here real quick. There's some warnings that whenever you're doing analysis are useful to know, but whenever you're doing visualization can be annoying. So if you are vecting things and there's a critical point or something like that, you'd like to know that, but I'm turning some of those warnings off so they don't keep popping up and telling me that there might be some critical points. I'm also going to draw things a little bit differently, so set a different color table, for example. And let's see what else we're going to do. Yeah, that'll be it. Okay, so I can draw this. All right, so let me zoom out here. And let me actually set these. I'm going to set those to tubes too, so you can see them a little bit better on this. All right, so you can see them a little bit better. Okay, so there are my 12 points here on my inlet where I've sliced. That's where I set up my seeds to be. And again, the streamlines give me an instantaneous view. Assuming that this was a steady state simulation, that's how these particles would advect. So you can see that situation changes a lot over time. This isn't a steady state simulation, right? So there's a lot of dynamics going on, CFD going on here. So what we really want is we'd like to know that if we put those points in at the beginning of our data, where are they going to end up at the end of the 200 time steps? And for that, we're going to use pathlines. So pathlines are also available through the Streamline plot. There's an option here under Advanced that says, would you like to do streamlines versus pathlines? So we're going to change that and do pathlines. And there's two important options here. So in order to do the advection, it needs to map these meshes onto each other for each time step. In general, if you have topology changing, that's an expensive operation. But I already showed you that the computational domain doesn't change, just the fields are changing. So I can tell VisIt that the mesh is static. So if the mesh is static, that's a non-trivial thing. I can just difference velocity vectors from each time step very easily. If the mesh isn't static, well, then we have to map meshes onto each other. That's more expensive. So in this case, I'm going to tell VisIt that the mesh is static, and I'm going to hit apply. And again, it's back to frantically reading all 200 time steps of my data set, and now it's going to advect these. Okay, so here's where we ended up. So it's a little bit of a different picture. Here's where we ended up doing that advection. And I can actually, let me put the heads on here too, so you can see where the ends are. Yeah. So that gives you a better idea of how the fluid's flowing throughout these 200 time steps. So calculating the streamline itself is computationally intensive, right? I'm basically doing a physics problem where I'm advecting all these things over all these time steps. But what would be really cool is if I could animate this and animate these streamlines and kind of show an alternate view of this other than just playing this time step at a time. And I have a Python script that shows how to do that. So I'm gonna show you that Python script. It's right here. Really all this does is it takes advantage of the fact that I already have the plot set up, and it's going to set a crop. So I can crop those streamlines at any point in time. There's different ways you can crop it, but for this example. So I can set a number of time steps here that's completely independent of the time steps in my simulation, right? I'm doing a interpolation crop through time. And I'm gonna execute this. And the first time it's going to have to, since some things have changed, it's going to have to recompute the streamlines, and then after that, it will animate the streamlines. So let me go back to controls command where I have my Python script set up. And here it is. Let me get this out of the way. So if I run this, it's popping up the command line interface. Again, reading 200 files, getting the answer. And now you can see the animation. And the next time I play this, it just happens quickly because we're done. We've already calculated, and now all we're doing is really changing the visual representation of it. All right. So those are the things I wanted to kind of drive you through today. Again, there's additional hands-on things for you to play with during lunch or breaks or up until 9 o'clock tonight. I'll be here. Thank you very much. I'll be happy to answer any questions, and we'll get Andy up here soon. Yeah.
So how do you dump a data file once you have a Python script? Like you perform a series of commands on a certain primary variable such as pressure, and you calculate like gradients of pressure. So how do you dump out the data file? Sure.
So I showed you how to save a window which creates a picture, but you're asking about how now that you've done something, you'd like to create the data set out of it. So I won't show you with the expression, but I'll just show you in general. So under File, Export Database, and similarly in the Python command line, there's an export database call. This allows me to basically export whatever the bottom of my pipeline is. So if I've done something, like I said, I've created mass, I could go in here and I could say, well, I would like to export my mass, and I can select different file formats that I like to go to, like VTK or Silo, for example, and run that and hit export, and after that I'll get the files out that have those extra data variables in them.
So I have another follow-up question. So, so if you create an isosurface and you set up a series of isosurfaces, and I want to dump the data from series of isosurfaces. Like for example, an isosurface value has like 10, and the minimum and maximum value. So I want to dump a data. So how do you do that?
So you'd like to isosurface the data and then export the values on the iso?
Yeah, export the values of the cells.
Yeah, so you can do that using this mechanism. If you do an isosurface and you do a pseudo-color plot, so you can do an isosurface on, say, temperature and pseudo-color plot of pressure, you could export both that temperature and pressure as variables. If you want to process it by hand, you probably want to get it to VTK, like a ASCII VTK file or something like that. But all those values will, so after you've done that operation of slicing it, when you export, that's what you'll get. So it's not just the derived quantities, it's whatever you have at the bottom of your pipeline. Does that make sense? Cool.
Do you have any plans of moving away from the standard jet and hot color burst to something that's more like perceptibly uniform or something more advanced? Yeah,
so we have a lot of better color tables in there. We also have a ticket to add Viridis, which is a new color table that people are using a lot. We haven't done it yet. I think we're gonna put Viridis in soon. Whether we make the default, I don't know. I think it's good to change to a better, more perceptive color table. I also think in 3D things are a little bit different than in 2D, so there's some tweaks there. Also, quite frankly, if people have been making plots for 10 years, they might have, they might want to keep making those same plots year after year with their same horrible color table. So we have to be sensitive to that. But yeah, I mean, it's on our radar. So yeah.
Additional question for Cyrus?
Can you use a kind of unstructured color map? Like I can find them in like a tech plot and Pariview, but I can't find it in VisIt.
So what do you mean unstructured color map?
Like you want to show all the current values, but you want to highlight some values.
Yeah, I mean, so there's a couple different ways you could do that. There's a lot of color tables that might help you do that in here. So let me just go to the color tables menu. Like, there's tons of them. But there's also a way you can do log. Basically, when you do a pseudo-color plot, you can do a log, or you can pin the min and the max so for just the range that you care about, or you can do a skew. So I'm not...
Yeah, I'm not like I want to show the minimum, but I want to highlight some level that's near the maximum, for example.
Yeah, so you could set the minimum to whatever you want it to be, and you can set the maximum underneath that, for example. Or you could threshold it out of your data set completely. I guess maybe we should talk offline, because I'd be interested to know. There should be some combination of things that can do what you're looking for.
Yeah, we can talk more.
Sure.